So today I want to look at two kind of unrelated problems from the Math magazine. And the first one has to do with placing weights on an octagon. Well, let's look at all the details. So let's place 8 weights with rational masses given by the numbers m1, m2 up to m8 on the vertices of a regular octagon. And then let's also assume that these masses, the mi's, are chosen so that the center of mass of the octagon, or the centroid, is at the center of the octagon. So what that means is that the masses are chosen so that you could balance the octagon on maybe your finger from the center. That's how you want to think about this. And let's show that given all of these conditions, that m1 equals m5, m2 equals m6, m3 equals m7, and finally m4 equals m8. So in other words, the masses across from each other are the same. I guess I didn't, put into this problem exactly how those masses are laid out in the octagon, but we'll assume that, m1 is across from m8 and so on and so forth. Okay, so the idea here is to maybe think that this octagon is inscribed in a circle of radius 1. In other words, it's inscribed in the unit circle. And then what we'll do is notice that each of these vertices is now a distance 1 from the origin. And now let's introduce some notation. So let's say that mass mi is at the point which we'll maybe call AI. And AI is in the real plane, just based off the fact that we're putting all of this into the Cartesian coordinate plane. And then, well, let's also get on the board that we are assuming that the octagon has so-called radius 1 and is centered at the origin. Of course, like the radius of an octagon, well, could take on a couple of different meanings, but we're assuming that it means that this is inscribed in a circle of radius 1 like we talked about before. Okay, and then next up, let's set an orientation. So let's orient so that we know that A1 is the point 1, 0. So in other words, that's along the x-axis. The point A1 is along the x-axis. And then, well, let's maybe just follow that orientation. So that means that A3 would be along the positive y-axis, and then A5 would be along the negative real axis, or sorry, the negative x-axis. And then let's see, A7, that would be along the negative y-axis. So that takes care of A sub odd, if you will. And now we just have to figure out, well, what about the rest of them? But let's observe that all of the rest of them make a 45-degree angle from the major axes, the x-axis and the y-axis. And that's just based off of the fact that here we have a regular octagon. But luckily, we know exactly the points that lay 45 degrees from the x-axis and the y-axis using trigonometry, given the fact that we're all within the unit circle and cosine and sine of 45 degrees or pi over 4 radians is well known. So that means that, well, we can fill in A2, A4, A6, and A8 pretty easily. So let's observe that A2 is the point 1 over root 2 comma 1 over root 2. That's because, well, it lays in the first quadrant between, let's see, A1 and A3. And then, let's see, we know that A4, well, that's going to be something like minus 1 over root 2 and then 1 over root 2. A6 will be minus 1 over root 2 minus 1 over root 2. And finally, A8 will be equal to 1 over root 2 and then minus 1 over root 2. Okay, so I think that's looking pretty good. But now let's recall that the centroid, or the center of mass of a situation, if you will, or an object given only point masses at certain points in the plane is really just like a sum of those masses at those points. Well, here we've got points. Well, what do you mean by a sum of points? Well, we want to think about it as a sum of weighted vectors. So the center at the origin has the following meaning, or the centroid at the origin, at the center of the octagon, has, like I said, the following meaning. So we have m1 times a1 thought of as a vector plus m2 times a2 thought of as a vector, and so on and so forth up to m8 times a8 thought of as a vector. And that's got to be equal to the origin thought of as a vector. In other words, the vector 0, 0. But now what we can do is take this big linear combination of our vectorified points and expand all of this out using the fact that we know what these points are and we know what the masses are as well. So that's going to give us something like this. We're going to have m1 plus m2 over root 2, and then minus m4 over root 2. And then let's see, it's going to be minus m5, and then minus m6 over root 2, and then plus m8 over root 2. So that's what we're going to get from the first entry. And then for the second entry, we're going to have something like m2 over root 2, and then plus m3, and then plus m4 over root 2, and then minus m6 over root 2, and then let's see, it's going to be minus m7, and then finally minus m8 over root 2. And like I said, we need this to be equal to the origin. That would put the centroid at the center of the octagon. The octagon is centered at the origin. But now let's observe, that means that this linear, or this combination of m1 to m8s in the maybe first entry as well as the second entry, both are independently equal to 0. So that's going to give us a system of, well, it looks like 2 equations, but we'll actually turn it into 4 equations. So let's see what we have here. We'll have m1 minus m5. And then after that, we'll have plus 1 over root 2. I'm going to factor all of that out. And then I'm going to group this in a way that looks kind of silly right now, but it'll be helpful. m2 minus m6. And then minus m4 minus m8. Okay, so we've got that is equal to 0. That's from taking the first entry. And then we'll do the same kind of thing for the second entry. So let's see, we're going to have m3 minus m7, and then 1 plus 1 over root 2. We'll have another m2 minus m6, but now it'll be plus m4 minus m8. And that's all equal to 0. But now let's go up here and look at something that we haven't used yet, and that is the rationality of the weights. So these weights are rational. But notice that means that I have a rational number plus 1 over root 2 times a rational number equals 0. And that's for both of these cases. But that in fact means that, well, the stuff not attached to 1 over root 2 must be equal to 0, and the stuff attached to 1 over root 2 also has to be equal to 0. And that's simply because 1 over root 2 is irrational. So that gives us a couple of more equations. So observe that we have m1 minus m5 equals 0. In other words, m1 equals m5. And then we have m3 minus m7 equals 0. In other words, m3 equals m7. And then we've got some stuff from the irrational part, the 1 over root 2 part. So we're going to have m2 minus m6 is, let's see, equal to m4 minus m8. So that's from moving things around in this first equation. And then we also have m2 minus m6 is equal to, well, let's see, it's going to be negative m4 minus m8. In other words, m8 minus m4. But let's look. That means that m2 minus m6 is equal to something and it's negative. But the only thing equal to something and it's negative is 0. So that gives us that these must be equal to 0, leading us immediately to m2 equals m6 and m4 equals m8, which is where we wanted to end up. All right, so let's maybe do that second problem. Okay, so the next problem is a limit, and it looks like a limit that would be pretty straightforward, but it's going to involve a trick. That being said, the trick will make this thing evaluate very, very quickly. Okay, so it's the limit as x goes to 0 from above of x over the square root of 1 minus e to the minus x squared. And I'd like to observe if we set x equal to 0 here, we have an indeterminate form of type 0 over 0. And well, a lot of times if you have that type of indeterminate form, you might want to use L'Hopital's rule. But notice that's going to transform this thing into the limit as x goes to 0 from above of, and I'm just going to do the calculation very quickly. So we're going to have minus x times e to the minus x squared over 1 minus e to the minus x squared to the 3/2. But not only is that an indeterminate form of the same type, but it looks actually more complicated. So applying L'Hopital's rule made everything more complicated instead of having a simplifying effect. So that means we need to have some sort of other trick. Okay, so maybe what could we do here? Well, let's maybe suppose that the limit exists and see what the value would be if it exists, and then we'll prove that it has to exist later, but that'll be pretty straightforward. So if we set the limit equal to L, so in other words, we have L is equal to the limit as x goes to 0 from above of x over the square root of 1 minus e to the minus x squared, then we know that L must be bigger than or equal to 0. How do we know that? Well, let's observe that for all values of x that you could plug into this function, you would get something positive, or I should say positive, because you can't get 0 by evaluating this at x equals 0 because we have an indeterminate form. So for all values of x that are positive, you get a positive output here. But that means that the limit, it doesn't tell you the limit's positive, but it tells you the limit is bigger than or equal to 0. It could be infinite though. Okay, nice. So now where would we go from here? Well, let's observe that we've got this square root in the denominator, and that actually caused difficulty when we applied L'Hopital's rule. So perhaps we could square this limit, and that would give us something nice. So let's square this limit, but that's going to be the limit as x goes to 0 from above of x squared over 1 minus e to the minus x squared. And that's just because the squaring function is continuous, so you can bring it inside of the limit. Now what could we do? Well, now we could apply L'Hopital's rule because this is a lot nicer now. So let's do that. So applying L'Hopital's rule in this case, we'll have, well, derivative of the numerator is 2 times x, and the derivative of the denominator is 2 times x times e to the minus x squared using the chain rule. But pretty clearly that 2 times x cancels, and then we can bring the e to the minus x squared to an e to the x squared in the numerator. And now we've got a continuous function. We can just apply x equals 0, and we'll see that we get the number 1. But let's see what we have here. We have that the limit squared is equal to 1, and we also know that the limit is bigger than or equal to 0. So what that tells us is that the limit must in fact be equal to 1. And that's a good place to stop.